Hello again, this is the Pencrest High School AP Physics C video series. This is video 5D, angular momentum. So we're already familiar with linear momentum, P equals mv. Objects that are rotating also have momentum, that's called angular momentum. Again, knowing the analogies for mass and for velocity in a rotational sense. The symbol for angular momentum is a capital L. It is a vector quantity. It has the same sign convention as the rotational kinematics variables or torque. That is, in the plane of the page, counterclockwise, angular momentum would be in the positive z direction, and clockwise angular momentum would be in the negative z direction or into the page. So this formula, L equals I times omega, is generally used for rotating solid rigid bodies with physical dimensions. We'll get to particles shortly. Again, rotational inertia has units of kilogram meter squared. Omega is radians per second. The radians disappear, and we are left with kilogram meter squared per second, which are the accepted units for angular momentum. The classical example that's used to show conservation of angular momentum is a figure skater who goes into a spin with her arms extended and one leg extended as she draws her arms in towards the rotation axis, which kind of goes vertically upward through her body. Her rotational inertia decreases. Since the angular momentum is conserved, the angular velocity must increase, and she spins faster. You'll find in cases like this that the kinetic energy is not conserved. When the skater pulls her arms in, the kinetic energy increases because it scales with omega squared. It would seem like you're getting additional kinetic energy from nothing, but however, the work done in redistributing the mass, right? So you're pulling the mass in closer to the rotation axis, and that work done in the redistribution is converted into additional kinetic energy of the skater. You would also use conservation of momentum, conservation of angular momentum in cases where independent rotating objects are brought together or coupled into a single rotating object, sort of like a rotational version of a completely inelastic collision. You would find each object's angular momentum before the collision, add them to find the system angular momentum, and then after the collision you would add the two objects' rotational inertias, like adding the masses in a linear collision, and then you would solve for the final angular velocity. Just like in linear collisions, the system must be isolated in order for angular momentum to be conserved, so we can't have external forces or torques acting on it. A standard example is when you have a disk of rotational inertia I1 that's already rotating at some omega naught. You drop another disk on top of it that has rotational inertia I sub 2, and then after the collision, so to speak, the two objects will be rotating with some other angular velocity omega. but the angular momentum of the system is conserved. Okay. Now, when we look at a particular, we look at a particle or a point mass that's moving with some velocity v with respect to a fixed origin, we're going to see that its angular momentum is given by r cross p. R is the position vector with respect to the origin, and p is the object's linear momentum. As long as the line of action of the object's velocity doesn't pass through the origin, that object will have some angular momentum. So an easier way to consider this angular momentum is to think of the perpendicular distance between the direction of the velocity, or its line of action, and the rotation axis. In practical terms, this is the closest that the particle will come to the rotation axis. In the image that you see here, this particle has a linear velocity v1 that's sort of in the positive y direction. We want to know its angular momentum with respect to the origin, or effectively with respect to the z-axis, which points out of the page towards you. We can see that the line of action of m1's velocity comes within a distance d1 with respect to the origin. So this perpendicular distance here is the one that matters in terms of the angular momentum that this particle has. So very simply, m1 v1 is the linear momentum of this particle m1, and it comes within a distance d1 of the rotation axis. So we use that as the perpendicular distance, and very simply m1 v1 d1. Okay, considering the direction of this angular momentum with respect to the origin, again, using the right-hand rule is the easiest way. You should be able to see that the angular momentum points out of the page towards you when you point your hand in the direction of R and then curl your fingers in the direction of V. R is to the right, V is vertically upward in the plane of the page, and your thumb points out of the page towards you, so it has a positive z direction or k direction angular momentum. Okay. Now, frequently what's going to happen here is that we'll have a system of objects in which one of them is a particle and has a linear velocity, and there's some sort of collision with an object that can rotate with respect to some fixed rotation axis. So in this case, we have a rod that is pivoted about some distance d from one end. So here's the pivot point, here's the rotation axis. And then we have a particle here, m2, that's moving with some linear velocity v. There's going to be a collision. M2 is going to hit the rod, and it could conceivably bounce off. It could stick to the rod. Either way, we're going to have a rigid rotating body after the collision. So what we need is to determine the angular momentum of the system before the collision, assuming the rod isn't moving initially. This is the angular momentum of the point mass, or the particle, with respect to that axis at a distance d from the end of the rod. So after the collision, the rod is then going to move with some angular velocity omega. We would use I omega for its angular momentum. The I, of course, is with respect to that pivot point, which would require us to use the parallel axis theorem. In any case, the angular momentum of the system is conserved, so before equals after. And again, depending on if the collision is bouncy or completely inelastic, we may have different conditions before and after, but the angular momentum is conserved. You could conceivably be looking at this system from above, in which case the rod is going to rotate in a horizontal plane, or you could be looking at it from the side. We want to talk a little bit about how the analysis would change. If you're looking at it from the side, it gets pretty complicated, because then after the collision, the rod will become an object that swings vertically. We know something about objects that swing vertically. Can't use rotational kinematics, but you can use the conservation of energy. So part of the key here is to know that you're going to be using the conservation of angular momentum to the collision only. So in other words, it applies right before the collision and right after the collision. But when we start talking about what the rod does after the collision and it swings vertically, now we need to make considerations for the conservation of energy. Okay, so collision means momentum, but swinging vertically means conservation of energy. Okay, so that's angular momentum. Next up is rolling and rotation. We'll have a couple of videos there, and until then, enjoy, and I'll see you again next time.